Hello and welcome to the Turing podcast, your new one-stop audio shop for all things data science, artificial intelligence and machine learning related from the Alan Turing Institute. This first episode was recorded a couple of months ago before we all had to spend so much time getting our heads around remote working and social distancing and actually significantly less air travel. So we thought it might be interesting to start with an episode that provides some fascinating insight into how things usually work in the skies. However, this was recorded before the current pandemic and we'll be releasing subsequent episodes in a slightly different order, with the next one being a discussion on how data science is supporting COVID-19 efforts, not the AI arsenal mentioned at the end of the episode, which will eventually be released. We hope you enjoy this new podcast, and of course we encourage you all to stay home and stay safe at this time. In the meantime, like, listen and subscribe on all your platforms. Let's get started, shall we?
You're listening to the Turing Podcast, a production of the Alan Turing Institute, the UK's National Institute for Data Science and Artificial Intelligence.
Hello everyone and welcome to the Turing Podcast. I'm Ed and I'm here with Tarek.
Hello there.
And today we've got a fun episode for you. We're going to be talking about AI for air traffic control, specifically a project that's been worked on here at the Turing Institute, involving AI to hopefully get more planes in the sky. But before that, we're going to have a quick discussion of some of the data science and AI topics we've seen in the media. I'm going to kick off with an article I've seen in the Telegraph. The headline is, NHS experiment in AI will see a whole city offered virtual hospital appointments by diagnosis by chatbot. The city in question is Wolverhampton. Basically, everyone there is going to be given access to an app. They can book GP appointments on this app, some of which will be offered remotely via the app. And a nice feature is that the patients will be able to play back their GP consultation so they can rewatch that video.
Interesting. So everyone's gonna be given access to this application.
Everyone in Wolverhampton, yeah.
Interesting. Even the folks without a smartphone, they're going to be given an app. And
that's a good question. Yeah. How do you define everyone in this case?
Indeed.
So there's a private company involved called Babylon who are going to be working in tandem with the NHS. And their big claim is that they're going to use their AI system to assess symptoms and offer diagnosis in some cases.
Indeed. Right. Okay. So this is quite an interesting one, because does this mean the end of the traditional GP? Everything is going AI.
Well, how good can these AI chatbot doctors be? I guess the proof is in the pudding. We'll see. Indeed.
Yeah. Looking forward to seeing that in action. For myself, Ed, I've got a fascinating story announced by Google the other day, actually, of their new chatbot, Mina. And apparently this new chatbot is working towards human-like chatbot that can chat about anything.
It's a bold claim.
Bold claim, indeed. And, apparently Google's Mina's model focuses on the understanding the context of a conversation to provide a sensible reply. So whatever that sort of means.
I don't feel like Alexa understands the context.
No, indeed. Yeah, exactly.
My conversation with her.
your long and fruitful convos in the evening, that you're not getting the replies you want.
But Mina will.
Mina will, apparently. And the goal is to create something that can, chat about anything a user wants. For example, 2 conversations showed that, you can ask Mina for show recommendations, and there can be meaningful replies as well as jokes and conversations like this. So, it looks like we're truly about to pass the Turing test.
The Turing test, yeah.
Yeah.
Developed to test whether an AI truly, can convince a human
Indeed.
that it's a person.
Yes,
I'll tell you what, we'll have to get Mina on the podcast.
Yes, we'll get Mina on it for...
See if she can pass for a realistic guess.
Yes, exactly, and that'll be the proof.
All right, well, that's it for today's media roundup. Next, the interview.
Hello, we're here with Radka Jersakova, Senior Research Data Scientist here at the Turing. She's been here for a number of years working on various projects. And we're going to talk to today about a very interesting project called the NATS project. NATS is for the National Air Traffic Services, I think. We'll double check that. Yeah. And yes, I guess, first of all, Radka, what is the project? What's it all about?
So NATS is in charge of air traffic control in almost the entire UK airspace.
Yeah.
So they're the guys sitting in front of a screen, watching the planes fly across the UK, telling planes where to fly higher, change their heading to make sure that all the planes pass through the UK airspace safely.
Right. So these are the guys up in the tower directing the planes.
Exactly.
Got you. Cool.
As you can imagine, it's an incredibly complex and difficult task and a very high-stakes task. And the thing they're interested in is exploring whether there's space for algorithms to support the work of air traffic controllers and sort of help them in kind of the complex decision-making that they have to do.
Yes, because it's a very stressful sort of job, right? It's supposed to be one of the most stressful jobs you can have. So I guess, for any sort of thing that can assist the air traffic controllers, that's what they want. So I guess what was the hope for NATS to sort of what did they hope that the Turing could provide insight into?
Well, it's really it's a research project, so the question was as open as, are there any algorithms which could help us in this space, which is very complex. As we sort of said, you're making very complex decisions in real time, which is quite a hard problem to tackle for people and for machines.
Yeah.
So really, they just were interested to explore what are the possibilities, what is out there, what are sort of the pros and cons of the different available approaches. So, the idea was to do this exploration. The starting point was, let's take a simulator of air traffic control, starting with some very simple simulations, and see if we can find algorithms that could handle very simple scenarios in a simulation, and learn from that what the available approaches or even sort of cutting-edge approaches can do and can't do.
Indeed. So, and this simulator that you mentioned, this was an open source simulator, right? Blue Sky.
Yeah.
So is this a simulator that the NATS guys use themselves, or have they got their own simulator sort of in-house that they're using for training these kind of things?
Yeah, so they have training simulators that they use for training humans. But kind of the way these are built, we can't work with them in the way that we need to. So that's why we chose this open source simulator, which really just simulates air traffic control. Kind of the purpose of this Blue Sky simulator isn't to train people in doing air traffic control. It is yet to kind of simulate real life air traffic scenarios.
Can I just throw in a tangent question?
Yeah, go.
Please.
What do you mean by open source in this context? What?
Right. Oh, okay. I'll take the floor on that one. So Blue Skies is an open source simulator, and what this is that the source code for this simulator is completely available. Now, it's also open source in another, shall we say, frame, in that it openly accepts contributions to the source as well. So, things that you might see could be a useful benefit to the package, or, things that might identify as an issue, you can contribute and hopefully improve this simulator.
So any software developer can come along.
Yeah, anyone can just
have a go at making it better.
Exactly. And so I believe, this was the sort of the simulator that you guys started with, right? So you wanted to have something that you could easily sort of mold to your liking and easily build upon. But I'm very aware that NATS have their own sort of simulators that are, I guess, a lot more sort of technical. They've got a lot of their in-house sort of things going on where they can attach their own sort of metrics and things like that. Because I know that was something that we discussed quite a lot in how, when you're trying to figure out what kind of algorithms to use, deciding what metrics you evaluate them against is very important. So can you tell us a bit about what kind of metrics that we've sort of like looked into?
So before answering that question, I'll just take a step back. I think at this point it's worth pointing out that what we found with this project, which is true with a lot of projects, is that, often a starting point, and really like the big part of project is defining what actually it is that you're doing. Yes. So we find, yes, there is a simulator of air traffic control that we can use, but what is a realistic air traffic scenario? That isn't necessarily obvious, in the same kind of, how do you measure performance of air traffic controller? And actually, when we kind of look at how air traffic controllers
It's making sure the planes don't crash, right? I mean, that's the main...
that is the starting point.
Yeah.
And definitely, yes, that is the main objective. But actually, so NATS helped to identify sort of metrics for air traffic control where, yes, so kind of safety, they call it loss of separation. So making sure that planes never get too close to each other, and, there's kind of defined distances they're ever sort of allowed to, how close they're allowed to get.
How close is too close?
I can't remember.
It's they have a defined distance.
Yes, there's a defined vertical and horizontal distance. So and whenever planes get, and even that distance is defined to be very broad. So kind of if two planes reach that distance, they're still quite far away from each other. But if that ever happens, they would have to report it. So kind of planes never get into that region at all. But there's a lot of complexity on top of that. So you want to make sure planes don't get too close to each other, but you also want to allow planes to kind of, you don't want to send them too many commands because that's quite annoying for the pilots. You want the flight to be fuel efficient. So that can mean if you at high altitude, you need to descend as late as possible. So there's all, you want the flight to be as smooth as possible. And as much as possible, keep planes on their kind of existing path. So there's all these other criteria, that ideally you want to be optimizing for, as well as this main objective, which is ensuring safety. And
I can imagine that they're trying to, make the route as efficient as possible and optimize.
Exactly.
But within those decided safety bounds.
Exactly. And then the next, so that's kind of the starting point. And I think if you train as an air traffic controller, you might first just care about safety, and kind of as you progress through training, you start caring for these other objectives. Eventually, you want to get to a point where not only do planes never get close to each other, but in the sector you're kind of controlling, there's never potential for two planes to get that close. So kind of the way, like good air traffic control means that if something, if I'm an air traffic controller and something should happen to me right now, the kind of state of planes in my region is such that the path that they're on wouldn't allow them to get close to each other. So it's not even like, are they too close to each other now? Mm-hmm. It's really, if you look at their paths, they would never get to that distance within each other in an hour's time.
Have you had a go at playing with the simulator yourself as a trainee air traffic controller? Put yourself in their shoes.
So
before you try and automate their jobs.
Yeah, I don't think I had the chance, but didn't yourself or perhaps Tim, another member on the project, they got to have a go? Yeah,
so we went to visit NATS and they showed us a training simulator, and one of our colleagues got to sort of try out a training scenario. And it was amazing.
You didn't get to have a go?
Huh?
You didn't get to have a go?
I found it too intimidating. And there's really, there's so much to keep track of because the other thing is, not only, is making sure the planes aren't too close to each other, all the planes have a place they want to get to. So you're trying to, which might mean they want to change altitude, they want to change direction. So you also have to keep track of where they are and whether they're kind of, you're allowing them to head to where they eventually want to exit from your sector, for example. So you're constantly scanning the planes, and there's more and more incoming, and you're kind of making sure. There's just so much to keep track of.
Yeah. The key thing here sounds like the instructions are coming in both directions, right? They're coming from the planes and they're going to the planes from the air traffic controllers.
Yes. And actually, it's not even that they're coming from the planes, but you do have each plane's route kind of in front of you. So if you sort of sit down and in front of a screen, you have information kind of each flight's plan. So kind of you know where they want to get to. And so ideally, you're letting them follow that plan, but kind of interrupting them as little as possible to ensure safety. So there's a lot going on. There's a lot of complexity. And so kind of going back to your earlier question, when you still want to do research in this domain, there's a lot of questions around, how do you evaluate performance? What does it mean? There's a lot of things you want to capture, but even what is a good training scenario? So you asked me, have I played around with a simulator? It's it's really easy to start up a simulator and just create a few planes ahead and fly around. But actually, there's again a lot of complexity of creating scenarios that are interesting. There's actually something to solve in a real world sense. Does that make sense?
It's difficult to simulate the realistic scenarios.
Yes, because you actually need to understand what real life air traffic control looks like. Because what a simulator allows you to do, the simulator allows you to sort of say, I want 5 planes, flying west to east at these altitudes, at these latitudes, whatever. But it's a big jump from there to this is what real life air traffic control looks like. Usually there's this many planes in this region, kind of at this distance from each other, and there's a lot of different types of conflicts you might want to solve. So again, kind of you have
Can
to
they not bring in some of that real information from the real air traffic controller situations just to train the simulator or train the air traffic controller, people who are learning to be air traffic controllers?
Yeah, so I think this is what they do when they're training the actual sort of the ATCOs, the air traffic controllers, when they're going through their college, and they'll get these sort of realistic scenarios. Now, the thing is, it's when it sort of comes to trying to sort of solve this in a research setting, it's like, how do you model that in sort of the simulator itself?
So it's worth saying that, yes. So at the moment, when people are trained on these scenarios, they're trained on scenarios created by humans. So you have already trained air traffic controllers, which can, so using their knowledge, create real-life scenarios of different levels of complexity that capture specific types of conflicts that they want people to solve. But there's only really few of those scenarios that exist. And ideally, we only ever want to use those scenarios for like our testing. If we ever have an algorithm which sort of tries to do this, we want to test them against those scenarios. For machine learning, the kind of sort of task we're looking at where you want to train an algorithm, ideally you need a lot of scenarios to train on, which you can't really create by hand. So then the thing, which again it's the kind of things that doesn't become obvious when you start a project, but you kind of realize actually, as Tarek mentioned, we need to maybe first off create a model of what is an air traffic scenario to maybe try to create a script which could automatically create a certain type of scenarios with a certain type of conflict. And that in itself is actually quite a complex thing to do. And actually, there is a couple of papers which came out recently which tried to look at this, air traffic control, using this, so using machine learning for air traffic control, using this open source Blue Sky simulator. But what we find if you look at it is that they don't do a good job of defining the kind of scenarios they're working with or the kind of metrics they're looking with. So it's really quite a complex thing to do. And one of the really interesting things about a project, and I think this is where the Turing really, for me, is an interesting place to be, is because, we work on a very research question with the industry. So kind of we get to do this exploratory research work, but with insight from people who actually know what it looks like in the real life.
All right.
And that's just a really invaluable thing.
They can come back to you and say, that's not a realistic scenario.
Yes.
Exactly.
Yeah.
Or they can help by telling us what it is, that they're trying to capture in their training scenarios. What is the kind of, how do they evaluate people and so on. And that is invaluable.
Indeed, which is exactly what happened, isn't it? Like they came by and sort of, we sort of pitched some ideas for certain scenarios. And they sort of were able to sort of guide us to say, well, that's not necessarily realistic. This is probably what would happen. Getting that sort of domain knowledge guidance really sort of helped us sort of get to the point where we can then maybe generate some of these interesting scenarios that we can then use for machine learning.
Yes.
But just to sort of touch on that, we were saying we wanted to sort of develop algorithms and try and use sort of machine learning to sort of like handle this problem. Can you talk about the types of machine learning that has been investigated in this project?
You mean in the past or
well,
from us?
I guess, yeah, you can touch on sort of approaches that happened before. But I know for this one specifically, wanted to look at sort of reinforcement learning. I'd be interested to hear a bit more about that.
Yes, I think that's really one of the big breakthroughs that's made this topic interesting is kind of advances in machine learning and methods like reinforcement learning. Because before, I think that there have been a few attempts to sort of try algorithmic approaches in this space, and usually people have looked at things like optimization algorithms, so kind of trying to find optimal paths, numerically for
reinforcement learning. Remind me, guys, this is the kind of techniques that Google are using to
Solve
train
a game ago, and all this
AlphaGo
stuff,
and
indeed.
the ultimate chess programs. So this is a similar kind of approach you use for solving the problem of getting as many planes into the sky as possible safely.
Before, people were constrained by looking at optimization algorithms where you maybe already have to have quite a good model of what it is you want to achieve. And the kind of advance with reinforcement learning is that, how would you say,
does the goal not have to be quite so explicitly stated?
So I would say the goal has to be explicit, but maybe you kind of need a bit less of an idea of what's the best way to get there first.
Right.
It's the idea of reinforcement learning is that you have some generic algorithm which learns from experience, and kind of really the internals of the algorithm focus on how, as it accumulates experience, what it does with that experience. So kind of the prototypical example are games, and and the idea that if you want to learn chess, you play chess, and you through winning and losing, you slowly learn what best moves are, without really kind of having to have a concept of strategies beforehand. You discover them through exploring the game or the environment, and
well, hold on. There's a niggle here, because I'm thinking like the way that those algorithms would learn to play chess is by losing, whereas air traffic control, you can't lose.
Right. Well, thank God we got a simulator.
Yeah.
So that's where we sort of say
you can kill simulated passengers, just not the real ones.
Yeah,
right?
just not.
Right,
as long as it's not real ones, indeed.
I mean,
and I think
that's the whole point.
The way it sort of sits in here is that games where you want to maximize your reward. Here, the reward is, can you get planes to their destination efficiently and safely? And if you can maximize that, then you're training a good algorithm. And I think that's where reinforcement learning really was suitable for this sort of problem. But I do know it's absolutely a massive task. And even though we've made massive sort of advances with machine learning approaches to this problem, but I'm very aware it's a long journey. I know the collaboration with NASA is going to be a long one. But do you see sort of in the future that machines will sort of take over in this regard? Or do you see that because I know right now their primary focus is to have this as a tool, and a tool to assist the ATCOs. But do you think one day that the AI will take over?
So genuinely, we're nowhere close.
Nowhere close, yeah, exactly.
It's a long way to anything like that. Because again, you really can't underestimate just how complex a task it is. And especially with approaches like reinforcement learning, things like how do you measure performance are extremely important. And I think the one thing we noticed, for example, from talking to Nats, is that at the moment there's also a lot of heuristics in terms of how ATCOs are judged on their performance. And once you try to
build that into a software system,
exactly, or you just try hard to turn that into a metric function, that gives you one score. There's just a lot of intuition in the field that doesn't necessarily translate into a specific number. How do you combine safety with fuel efficiency? And the algorithms that exist are very sensitive to that. And really kind of at this point, we're talking about exploring very simple types of problems. Like there's a lot of complexity in terms of the types of scenarios you might encounter and how you train those algorithms, how you evaluate them. So I think there's a lot of problems to be solved even just in posing the right questions and defining the problem in a suitable way that I don't think have really been cracked.
Yeah.
Have any of the approaches tried so far? Do they look promising? Are they getting some good results?
Well, again, it's there's only been a few, and kind of the impression is that the scenarios they're looking at aren't really what air traffic controllers encounter. It's sort of they aren't necessarily even solving the right kind of problem. It's a very simple scenario that isn't at all realistic or kind of isn't really capturing the kind of decisions ATCOs have to make.
Is that the next stage to sort of build up the more realistic scenarios so that future AI models can have a better go at the real task?
So that's what I believe in. And I think it's true for. I think it gets quite underestimated how important it is to kind of create a good problem set. I think the areas where we've seen the most advance in machine learning is image recognition. And the reason for that is because someone first built a massive data set that was labeled, with images and set up a very clear evaluation metric. The kind of people but sort of allow people to sort of try the algorithms and evaluate the algorithms on. And suddenly you sort of start seeing really big improvements in performance. And I think, especially with complex problems like this, it's going to take a while to get to a point where you have a sort of well-defined task you want researchers to try to tackle. But I think that's one of the outputs of this project. So we're trying to move towards that.
Yeah, so I guess if you're working in image recognition, these data sets are available online. There's loads of them. There's loads of options. But if I'm not wrong, part of the platform you develop for your project should hopefully enable outsiders to develop their own AI models to tackle this chart. Is that right?
Yes. So this goes back to that idea of open source. So everything we're building for this project is open source. And the idea is exactly that we help to build a platform that should make it easy for people to try algorithms on, realistic scenarios in an air traffic simulator, and kind of to build the infrastructure that enables that, gives them a set of metrics to evaluate against, and kind of get people start thinking about tackling this problem.
So that would be the sort of like the future of the project sort of going forward, is to open this up to sort of the wider community and sort of get as much sort of collaboration as possible. I feel like the Turing has done a great job in developing the infrastructure to sort of make this sort of possible, and now it's sort of
now it's up to the wider world.
Exactly,
it's up to
the wider world to tackle this and hopefully come up with interesting ways to tackle this problem.
Is there a resource online that budding software developers can go to?
Indeed. Well, so everything is under sort of the framework of the Alan Turing GitHub under the Seymour project. That'll be in the show notes. It's
we'll put it in the show notes.
Exactly. Yeah, good on you.
But if you go to the Alan Turing Institute website and search for NATS, you'll come up with more information on this project.
Yes. You can read.
It is worth noting it's not quite complete yet.
Yes,
in progress.
Yes, it's very much in progress. But the hope is very much that we make it very easy for people to try tackle this problem with machine learning, reinforcement learning, and for me that's the exciting thing. Hopefully, kind of in next year we'll see a lot of people try different approaches in this space using this platform, and that'll be really, really cool.
Awesome. All right. Thanks very much, Radka.
Yes.
Thanks for joining us on the
Thank
podcast
you.
and telling us all about this awesome project.
All right. I hope you had a good time.
Yeah, had a very good time. Thank you, guys.
Cool.
Thanks again to Radka for joining us today. Join us next time where we'll be discussing AI for fantasy football. To learn more about the work going on at the Alan Turing Institute, visit our website at turing.ac.uk. To get in touch with the podcast team if you have any questions or suggestions, email us at podcast@turing.ac.uk.
Music for this episode was provided by Jamin Sun. You can listen to his latest releases at jaminsun.bandcamp.com.
The Turing Podcast is hosted by Ed Cowstry, Tara Callum, Ben Walden, Effie Dennis, and produced by Dan Whitfield for the Alan Turing Institute.